You stand at a fork in the road. One road pays now. It is short. It is easy. It looks safe. The other road pays later. It costs time now. It may open better roads after it. The hard part is not the fork. The hard part is that every road leads to more forks. That is the real shape of choice. Chess is like this. Retirement is like this. A factory is like this. A self-driving car is like this. A trading system is like this. You do not choose one move. You choose one move plus the future that move creates. Richard Bellman gave that idea a formula. V of S equals max over a of open brace R of S comma, a plus gamma times expected value of V of S prime close brace. Here, V of S is the value of state S. S is the state you are in now. Max over a means choose the action that gives the highest value. R of S comma A is the immediate reward from taking action A in state S. Gamma is the discount factor on future value. Expected value means the average over possible next outcomes. V of S prime is the value of the next state. S prime is the state you may land in after this move. It says the value of where you are now is the best reward you can take at once, plus the discounted value of where you may land next. This equation built dynamic programming. It shaped modern control theory. It made reinforcement learning teachable. It sits under value iteration, Q learning, AlphaGo style planning, robotics, inventory control, route planning, and portfolio choice with frictions. If you want to know how machines learn to plan, this is the hinge. Every child knows greedy choice. Take the candy now. Skip the homework. Save the hard part for later. Every adult knows the trap. The best choice right now is often not the best choice over time. A warehouse can ship the last spare part now. Then it may strand a bigger customer tomorrow. A trader can sell today to avoid pain. Then the same trader may miss the rebound that pays for the risk. A robot can turn left to avoid a chair. Then it may trap itself in a corner. A chain of choices is not like a one-shot choice. The first move changes the second problem. That sounds simple. It is not simple to compute. In the early 1950s, Richard Bellman worked at the Ring Corporation in Santa Monica. Ring was tied to military planning, logistics, engineering, and control. These were not neat textbook choices. They were chains of choices under short time and thin information. A planner might choose a route first. Then came a fuel policy. Then came a repair policy. A commander might choose a deployment now. That choice would change what could be done tomorrow. An engineer might choose a control input now. 1 second later, the system would sit in a new state. The computers were weak. The problems were huge. Bellman called his method dynamic programming. Dynamic meant the problem changed over time. Programming meant choosing a plan. It did not mean writing software. One of the key ideas in computing got its name before programming meant code. In 1952, Bellman described problems made of a sequence of operations. That was the pain. If each step gives only 2 actions, 10 steps already make 1,024 full plans. 30 steps make more than 1 billion. Then add uncertain outcomes. The tree grows faster than a person can even name its branches. Brute force says list every future and pick the best. Reality says you will drown before you finish the list. Bellman's question was sharper than that. Can we solve a long decision problem without carrying the whole tree at once? That was not a math game. It was a live planning problem. The military had it. Factories had it. Transport systems had it. Any system that moved through time had it. People tried local rules. Take the shortest path you can see. Keep the most inventory. Spend the least fuel. Pick the move with the best score right now. Those rules were cheap. They were also blind. They could not price tomorrow. Other people tried full enumeration. They wrote down all possible paths. Then they compared them. That worked for toy cases. It failed when the number of stages grew. The missing tool was a way to reuse future answers. If you already know the value of tomorrow's state, you should not solve tomorrow from scratch each time today points there. That sounds plain now. It did not sound plain then. Before Bellman, people could describe the burden. They could not compress it. They could draw the tree. They could not fold it into something a machine could use. This mattered because real systems live through time. Air defense lives through time. Inventory lives through time. Retirement saving lives through time. Medical treatment lives through time. Routing packets across a network lives through time. A choice now matters because of the state it creates next. That is why the idea moved far beyond applied math. It spread into economics. It spread into operations research. It spread into computer science. It spread into control. It spread into machine learning. It gave planners a way to turn a huge future tree into a smaller table of values. The best image is a road map folded into an index card. The card is not the whole map. It is the answer you need when you reach a place. That is the shift Bellman made. He stopped asking for the best full path all at once. He asked for the value of being here. Then he asked what that value must be if tomorrow will be solved the same way. The gap was plain. People could see the full future tree in principle. They could not compute it in practice. They needed one rule that made long-run choice feel local again. What is the value of a state if the future begins from that state? The first character is the state. A state is the information you need now. It may be a board position and go. It may be a warehouse stock level. It may be a robot's location and speed. It may be a portfolio with cash, holdings, taxes, and trading costs. The state is the world compressed into a decision-ready snapshot. If the snapshot leaves out something important, the formula cannot save you. The second character is the action. An action is what you can do from the state. Move a stone. Buy stock. Raise the thermostat. Ship the part. Brake the car. Explore a maze. Offer a price. Each action has a cost or reward now. The third character is the next state. After you act, the world moves. Sometimes it moves in a known way. Sometimes it moves by chance. The warehouse gets a new order. The car sees a pedestrian. The market gaps down. The opponent answers your move. That next state is written as S prime. The fourth character is the value function. V of S is the value of being in state S when you act well from that point on. This is the great compression. You do not store every future path. You store one number for each state. That number says, if you ever land here, this is what the future is worth. The fifth character is Richard Bellman. Bellman did not just give a neat recursion. He gave a way to plan. The future can be folded backward into today. The name for that idea is the principle of optimality. In plain words, it says this. If a plan is best, then after the first move, the rest must still be best for the new state. That sounds plain. It is powerful because it lets you cut the tree. You do not need to remember how you reached a state. If the state holds all that matters, the best future from there is the same future. A quiet condition hides inside that claim. The state must be complete enough. If the state says robot at hallway corner, but leaves out floors wet, the future from that state is not the same future. The missing fact changes the value. This is why the Markov idea matters. A Markov state is a clean summary. Once you know it, the past path adds no useful facts for predicting the future. The Bellman equation likes Markov states because they make recursion honest. Bellman's trick is like writing the answer on every room in a maze. Once you enter the room, you know how good the rest of the maze is. Now we can write the equation that turns this idea into a machine. Here is the formula. V of S equals max over a of open brace, R of S comma, a plus gamma times expected value of V of S prime, close brace. Here V of S is the value of being in state S. S is the current state. Max over means choose the action and that gives the highest value. A is an available action. R of S comma A is the immediate reward from taking action A in states S. Gamma is the discount factor between 0 and 1. Expected value of V of S prime is the expected value of the next state. Expected value means the average over possible next states. S prime is the next state after the action and uncertainty. The equation says one thing. The value of now equals the best blend of now and later. Immediate reward is the first part. Future value is the second part. The max operator chooses the action that makes the total largest. The discount factor gamma controls how much future reward counts today. If gamma is near 0, the system is impatient. It cares mostly about now. If gamma is near 1, the system is patient. It cares deeply about later. The expectation handles uncertainty. One action may lead to several possible next states. The formula averages those next state values by their chances. That is why the brackets matter. Inside the brackets, you score one action. Outside the brackets, you compare actions. This keeps two questions apart. First, what does this action create? Second, which action creates the best total? That split is the whole discipline. In Bellman's 1952 paper in PNAS, the object was a sequence of operations. By 1957, the book Dynamic Programming made this functional equation the standard language for multi-stage problems. Now picture a small delivery robot. The robot is in state S. It can go left, right, forward, or wait. Going forward may earn a small reward because it gets closer to the drop-off point, but it may also lead near a blocked hallway. Waiting earns little now, but it may let a door open. The Bellman equation asks a plain question. For each action, what do I get now, and what is the next state worth? Then it takes the best action. That is why this is not just a scoring formula. It is a planning formula. Here is a small numeric example. Action A gives 10 points now. Then it leads to a state worth 0. Action B gives 4 points now. Then it leads to a state worth 10. If gamma is 0.9, action A is worth 10. Action B is worth 4 plus 0.9 times 10. That is 13. The greedy action loses. The patient action wins. The fork is no longer a fork alone. It is a fork plus the future map behind each road. The equation turns think ahead into arithmetic. But the most important part is hidden. How can the future value already be known? Start with total return. Call it G sub t. It is the reward now, plus the discounted rewards later. G sub t equals r sub t plus 1, plus gamma times r sub t plus 2, plus gamma squared times r sub t plus 3, plus dot dot dot. Here G sub t is the total return starting at time t, r sub t plus 1 is the reward one step ahead, gamma is the discount factor, r sub t plus 2 is the reward 2 steps ahead, gamma squared is the discount applied for 2 steps, r sub t plus 3 is the reward 3 steps ahead. This looks infinite, but it has a recursive shape. Separate the first reward from the rest. G sub t equals r sub t plus 1 plus gamma times open parenthesis r sub t plus 2 plus gamma times r sub t plus 3 plus dot 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 close parenthesis. Here G sub t is the total return starting at time t. R sub t plus 1 is the reward 1 step ahead. Gamma is the discount factor. R sub t plus 2 is the reward 2 steps ahead. R sub t plus 3 is the reward 3 steps ahead. The expression in parentheses is the return from the next state. So today's return equals today's reward plus gamma times tomorrow's return. That is the seed. Now define V of S as the best expected return starting from state S. If you take action S in state S, you get an immediate reward R of S comma A. Then you land in the next state S prime. From there, the best future is V of S prime. So action has this total value, R of S comma A, plus gamma times expected value of V of S prime. Here R of S comma A is the immediate reward from taking action A in states S. Gamma is the discount factor. Expected value of V of S prime is the expected value of the next state's value. S prime is the next state after the action and uncertainty. If there are many possible actions, choose the best one. That gives the Bellman equation again. V of S equals max over of open brace R of S comma A plus gamma times expected value of V of S prime close brace. The equation is self-referential because a state is priced by the states it can reach. This is not circular in the useless sense. It is circular in the fixed point sense. You can start with rough guesses for V of S. Then you apply the Bellman update again and again. Each update pushes current values toward the values implied by their neighbors. That is value iteration. A terminal state is easy. If the game is over, there is no future value. The value is just the terminal payoff. Then values can flow backward. The winning square gives value to the square before it. That square gives value to the square before that. A goal at the end of a maze sends a signal backward through the maze. This backward signal is called a backup. A backup takes a reward plus a future estimate. Then it uses that pair to update a current estimate. In a small grid, you can watch the numbers change. At first, every square may be worth 0. Then the goal square gets value. Then the nearby squares learn that they can reach the goal. Then farther squares learn through the nearby squares. The value spreads backward through possible futures. That is why dynamic programming often feels like solving a problem backward. You price the end. Then you price the states that can reach the end. Then you keep backing up. Watkins and Diane proved a key result in 1992 with Q-learning. Their method was model-free, but its update still carried the Bellman idea. Current action value should move toward reward plus discounted best future action value. The action value version looks like this. Q of S comma A equals R of S comma A plus gamma times expected value of max over a prime of Q of S prime comma prime. Here, Q of S comma A is the value of taking action A in states S. R of S comma A is the immediate reward from taking action A in states S. Gamma is the discount factor. Expected value means the average over possible next states. Max over a prime means choose the next action, a prime with the highest action value. A prime is a possible action in the next state. Q of S prime comma a prime is the value of taking action a prime in next state S prime. S prime is the next state after the action and uncertainty. Now the value belongs to a state-action pair, not just a state. This helps when you do not know the transition model ahead of time. You can learn from experience. Try an action. Observe reward. Observe next state. Update the estimate. The Bellman equation becomes a target. Deep reinforcement learning keeps this target but replaces the table. Instead of a value for every listed state, a neural network approximates the value. That is powerful. It is also less exact. The old table gave clarity. The new function approximator gives scale. A reward at the end of a maze can teach every earlier square. It does so by traveling backward one update at a time. The formula is beautiful because it compresses the future. The wall is that you must describe the future well enough to compress it. The Bellman equation has 3 hard walls. The first wall is scale. Bellman later called it the curse of dimensionality. Each new state variable can multiply the size of the table. A grid with 100 positions is small. Add speed, direction, battery, cargo, weather, traffic, and other agents, and the state count can explode. Dynamic programming turns a tree into a table, but the table can still become huge. That is why modern systems use approximation. They use neural networks, fitted value functions, sampling, rollouts, and policy gradients. They often cannot store exact V of S for every state. The second wall is the model. The equation needs to know what an action does. What reward comes now? What next state can happen? With what chance? If those pieces are wrong, the recursion will still optimize. It will just optimize the wrong world. The third wall is reward design. The formula maximizes what you put into R of S comma A. It does not know what you meant. If the reward is too narrow, the policy can exploit it. A robot told to move fast may move in unsafe ways. A trading system told to maximize short-term profit may hide tail risk. A recommender told to maximize clicks may learn to feed outrage. This is specification risk in plain language. You asked for a number. The system chased the number. It did not chase your intent unless your intent was in the state, the action set, the reward, and the constraints. In 2018, an Uber self-driving test vehicle struck and killed Elaine Herzberg in Tempe, Arizona. Investigators found failures in perception, prediction, and safety process. A planning formula cannot choose safely if the state, model, and safety constraints misdescribe the world. That case does not mean the Bellman equation failed. It points to the deeper warning. Sequential decision math can only optimize the world it is given. If the state omits the human in the road, the max operator becomes dangerous. If the reward undervalues safety, the max operator becomes dangerous. If the model assigns the wrong next state, the max operator becomes dangerous. This also applies in finance. A portfolio rule can look optimal in a model with stable trading costs, normal liquidity, and known return dynamics. Then a crisis changes the state. Liquidity vanishes, costs jump. Correlations rise. The computed future value was built for a world that no longer exists. This is the practical portfolio wall. A Bellman setup can include trading costs, taxes, rebalancing bands, and drawdown limits. It can even price the option value of holding cash. But the equation is only as good as the state and transition law. If the model says liquidity is always there, it will not teach you what forced selling feels like. The original problem was how to price future consequences without listing every future path. The wall is that the compressed state must still carry the facts that make those consequences real. The formula is not a conscience. It is a mirror. It reflects the reward and model you hand it. So the trade is plain. Use Bellman thinking. But do not pretend the table is the world. The Bellman equation is not a magic planner. Inside a well-described decision problem, it is the cleanest lever we have. It is like a chess coach asking not what you can win now. It asks what board you will face after the reply. Use it when today's choice changes tomorrow's options. That is the first test. If there is no future state, you do not need Bellman. Use plain optimization. If the future state matters, Bellman may be the right frame. The second test is whether the state is good enough. Ask what facts must be present so the future does not depend on the path that got you here. In a board game, the board position may be enough. In a market, current holdings are not enough. You may also need liquidity. You may need taxes. You may need volatility. You may need borrow cost. You may need the regime. You may need hard constraints. Then comes the third test. Be honest about reward. Write the reward before you optimize. If you reward speed, do not act shocked when you get reckless speed. If you reward clicks, do not act shocked when you get clickbait. If you reward one period return, do not act shocked when hidden risk piles up out of sight. There is a fourth test too. Ask whether exact dynamic programming is worth it. For a small problem, a table may work. For a medium problem, value iteration may work. Policy iteration may work too. For a large problem, you may need approximation. For a messy real system, you may need simulation. You may need stress tests. You may need human limits around the learned policy. The Bellman equation gives you the spine. It does not choose the engineering. The equation is V of S equals max over of R of S comma A, plus gamma times expected value of V of S prime. Here, V of S is the value of being in states S. Max over a means choose the action with the highest value. R of S comma A is the immediate reward from taking action A in states S. Gamma is the discount factor on future rewards. Expected value of V of S prime is the average value of the next state S prime. Bellman's answer to the giant future tree was simple. Price states, not paths. If the future from a state is summed up by V of S, then today's best move is current reward plus discounted future value. Bellman's 1952 work, then his 1957 book, gave operations research a reusable method for multi-stage choice. Control theory took it too. Economists used Bellman equations to model saving. They used them for spending. They used them for growth. They used them for asset prices. Computer scientists used dynamic programming for shortest paths. They used it for parsing. They used it for edit distance. They used it for scheduling. They used it for planning. Reinforcement learning took the same recursion and turned it into a learning target. That line runs from Q-learning in the early 1990s to deep value functions in modern game systems. AlphaGo made the idea visible. The 2016 Nature paper joined deep neural networks with tree search. It used policy networks to suggest moves. It used value networks to estimate outcomes. People watching saw a machine look ahead in a way that felt strange. AlphaGo Zero went further. It dropped human game data. It learned from self-play. In the 2017 Nature paper, it beat the published champion, defeating AlphaGo by 100 games to 0. Do not shrink those systems down to the textbook equation. They are richer than that, but the family likeness is plain. Estimate future value, search actions, improve the policy, repeat. The same idea that helps solve a tiny maze also helps a Go engine look past the next stone. Here is the practical use tomorrow. When a choice feels hard, make 3 columns. State, action, next state. Then ask one question. What does this action make easier or harder next? That is Bellman thinking without code. For investing, the question gets sharper. Do not ask only, what is the expected return today? Ask what state this position creates for the portfolio tomorrow. Does it preserve cash? Does it raise forced selling risk? Does it create tax friction? Does it lock you into a bad branch? Does it keep optionality alive? The Bellman equation says the value of now is the best immediate reward plus discounted expected future value. It turned long chains of choice into reusable state values, built dynamic programming, and gave reinforcement learning its backbone. Use it whenever today's action changes tomorrow's option set, but never forget that the formula only sees the state and reward you define.